Good morning, students. Today we are going to continue the previous part. Okay, we have discussed the different types of case studies. The case study one is a distillation. The second one is a predictive maintenance in heat exchangers. So the objective is to develop a predictive maintenance strategy for heat exchangers using data-driven models aimed at detecting early signs of fouling. So the main problem in the heat exchanger is a fouling. So the hot fluid and the cold fluid has been allowed to pass so that the heat will be transferred between the hot fluid to the cold fluid. So during this process, because of the characteristics of the fluid which has been flowing inside the tube side or in shell side, obviously the fouling occurs. Usually the fouling liquid is allowed to pass through the tube side so that the bundles can be removed and we can replace the bundles effectively rather than the fouling fluid is allowed to pass through the shell side because the cost is much actually when the fouling occurs on the shell side. So that you are aware of it, that is a domain knowledge. Coming to the reducing unscheduled downtimes, so that is very important. So the unscheduled downtime, as I told you in the last class, will make them to maybe a cost effective process. I mean, make them more cost loss. Okay, so we need to be very precisely run the equipment. Okay, so that the cost of the process will be minimized. So optimizing the cleaning schedules to lower operational cost. So these are the objectives. Okay, during the running the heat exchanger effectively. Coming to the background, heat exchangers are essential in energy integration and process control in chemical plant. When you see heat exchangers, where and all they are used mainly for the energy integration as well as the process control, essential in energy integration and process control in the chemical plants. So one of the common operational issues is fouling. So when you see the hot fluid is allowed to pass from the thing, they are not let it out to the environment. Before, for example, even it is a pure water which is having a more than a normal temperature, atmospheric temperature, let's say 25 degrees Celsius or 30 degrees Celsius. Okay, so the normal temperature, okay, they are not allowed to let it out at a higher level more than that. For example, the water should not be sent out at 45 or 50 degree. Okay, so obviously that will hinder the affect the environment. Okay, so that the aquatic life which are present may be getting affected. Okay, so in order to avoid that, usually the energy will be taken out of the even for the pure water. That energy will be utilized for some other purpose. So usually it will be an integrated process. Okay, the energy integration, it will be in a chemical plant. They won't make you waste the energy. Okay, so that is a very important thing, and which leads to the decrease in heat transfer efficiency. One of the common operational issues is fouling. So why this is occurring? Okay, decrease in heat transfer efficiency. Okay, which leads to which leads to because of this fouling. What are the effects? Okay, decrease in heat transfer efficiency, higher energy consumption, risk of process disruptions. So why this fouling occurs? As I told you, the fouling fluid is allowed to pass. There may be a scaling. Because of that, the material may get corroded, folded. Okay, or else what is called a fouler, because of the fouling characteristics of the fluid, the fouling may occurs. Okay, so the traditionally fouling is handled with the periodic maintenance. So that is very very important. So the periodic maintenance in the sense they will keep on need to check actually the heat transfer efficiency. Okay, and things like that. Okay, usually when you try to design for example shell and tube heat exchanger, what are the things we need to keep in mind? The inner side of the tube side diameter. Okay, the inner diameter of the uh, tube side or outer diameter of the tube side, the inner diameter of the shell, outer diameter of the shell, how it has been pitched, the pitch. Okay, the number of baffles, the side pass, two shell, two side, two pass. Okay, these are the parameters which you need to think of in designing this. How much is the pressure drop on the tube side, how much is the pressure drop on the shell side. That are the factors which need to be usually need to think of, and how much is the overall heat transfer coefficient. Okay, heat transfer area and things like that. Okay, so the traditionally fouling is handled with periodic maintenance, which may be either too yearly unnecessary. Too early is unnecessary and too late is a causing failure. So the periodic method, exactly when it is needed, that need to be created. So you should not very frequently clean the things, so that it makes a cost, increase the cost unnecessary. Okay, if you do it in the early stages when it is more than required. Okay, or too late when you try to do the periodic maintenance very late, obviously that will cause the causing a too late, causing a failure of the process. Okay, the heat exchanger will not be effective. So the process overview, the case involves a shell and tube heat exchanger used in a refinery preheating unit. The case involves a shell and tube heat exchanger. So just now I told you two shell two tube pass used in a refinery preheating unit. Okay, so just imagine the particular process operating continuously with the heavy oil stream that cause organic and particulate fouling. So when you try to operate with the heavy oil stream, what will happen? Obviously, it will cause a organic and particulate fouling. So this may occur. So let's say I just now I told you, so fouler liquid will corrode the what you call the tube side and things like that. So if you are continuously passing a heavy oil stream, obviously that cause the organic and particulate fouling. So what are the data collection? So in the distillation column, we have seen different types of data which has been collected, like reflux ratio, what are the things? The feed composition, temperature, pressure, number of the pressure inside the distillation column. Okay, yeah, the pressure and the reboilability, condensability. Similarly, for heat exchanger, what are the factors which need to be done? So what is the inlet fluid? What is the outlet fluid? So what is the temperature? What is the flow rate of that particular fluid? The pressure drop which has been occurred during the shell side or the tube side. What is the U duty? Okay, what is the ambient condition? Maintaining the logs indicating the cleaning days. These are the data collection that need to be done actually for the heat exchanger. So why we are doing it? To make this process effective, and we now to know actually when the predictive maintenance is needed, whether it's needed on an exact time. That's what we are going to calculate. So this is a data collection. Hope you understood. 6 months of historical process data at 10 minutes interval is already done. So coming to the future engineering, so we have already seen in the few lectures back, okay, what is future engineering? I just would like to recall back the future engineering. So here we calculate the heat transfer coefficient using the relation Q is equal to UA delta T law. So the future engineering is a process of selecting, creating and transforming the data into relevant features for machine learning models. So it is a process of selecting, creating and transforming the data into features. Okay. So it involves transforming the raw data into format that is suitable and effective for model training, ultimately aiming to improve the model performance. Here I would like to highlight what it is. Okay, feature engineering is a crucial pre-processing step in machine learning. It involves transforming the raw data into features that is meaningful and useful for the model. This process can include creating new features, modifying existing ones, or selecting the most relevant ones. This we have seen actually in the previous classes. Just would like to refresh back the thing. So why it is important? The quality of features significantly impacts model performance. Okay, well engineered features can improve model accuracy and reduce computational cost. Future engineering helps models learn more effectively by providing them with the right information. So what are the key aspects of future engineering? Future creation, future transformation, future selection and dimensionality reduction. What is future creation? So I just would like to recall back. This involves generating the new features from the existing ones, such as combining features, creating interaction features or using domain knowledge. Future transformation includes techniques like scaling, normalization and handling missing values. Feature selection, this involves choosing the most relevant subset of features to be used for model training. Dimensionality reduction, techniques like principal component analysis can be used to reduce the number of features while preserving the information. So the future engineering is a process of selecting, creating and transforming the data into relevant features for machine learning models. So here we are taking a heat transfer coefficient, okay, calculated using the correlation and created derived features, okay, such as U-tube fouling resistance, efficiency loss over time. So the second point is random forest regression. Build a predictive model to estimate the fouling resistance. So the predictive model is we need to build to estimate the fouling resistance based on the previous data, that is a historical data. Future importance reveal that pressure drop, inlet temperature and flow rate are very key contributors. So it's like a dimensionality reduction. So these factors will have a more predominant features when compared to the others in dealing with the scaling, that is the fouling characteristics. So the pressure drop, inlet temperature and flow rate were the key contributors. Future importance reveal this. Okay, so hope you understood. Coming to the long short-term memory neural network, which I already told you is a recurrent neural network which has been used for the speech recognition as well as the tone tone recognition. Okay, the tone which how the tone need to be set. Okay, so this algorithm has been used in speech recognition. Applying LSTM, a type of recurrent neural network for time series forecasting, trained to predict the future fouling resistance based on the past behavior. Okay, based on the past behavior, previous data, we could be able to predict the fouling resistance. And the forecast horizon, and the forecasting means in future we can find it out up to 7 days in advance. Okay, so by using this model up to 7 days in advance with greater than 85% accuracy, we can be able to find the correct and when the fouling may occur. The key findings by using these algorithms, okay, clear signs of fouling occurred 7 to 10 days before performance drop. Okay, so before performance stuff, we know actually before 7 to 10 days. Clear sign of fouling occurred 7 to 10 days before, okay, performance drop. And random forest provided a good interpretability and long short-term memory outperformed in forecasting accuracy. Random forest provided a good interpretability, but LSTM outperformed in. So when compared to random forest and LSTM, random or LSTM outperformed in forecasting the accuracy. So random forest is a supervised learning, right? So the maintenance logs showed a mismatch between the actual fouling and the cleaning frequency. Okay, so the key findings, maintenance logs showed a mismatch between the actual fouling and the cleaning frequency. So the recommendation using the LSTM model in a real-time dashboard to monitor the predicted fouling values. So LSTM model is outperformed, so that we are taking that one in a real-time dashboard to monitor the predicted fouling values. Trigger cleaning only, trigger cleaning only when the predicted fouling threshold exceeds the critical value. Update model continuously using the new process data on learning. Okay, so these are the recommendations they are giving to in order to find the predictive maintenance. Okay, before just try to find it out when the fouling occurs and in with accuracy. Okay, so before the incident happened. Okay, and coming to this doing by this technique. Okay, before analytics and after analysis, the average cleaning frequency for every 20 days. For example, we are unnecessarily cleaning every time, so that will cost much, right? So every 20 days, but the required after analytics by using the machine learning models, what we found is that 32 days once if we clean the process, that means the heat exchanges, that will more good, more good. I mean, good enough. Okay, rather than going at a shorter period. When you try to do it in a 20 days frequent, obviously that is a cost effective. It's not cost effective. It's not cost effective. Unscheduled downtime 3 to 4 times per month. So just imagine, okay, per month that is the equipment has need to be cleaned for 3 to 4 times downtime period. And it's a loss for the company, right? So that for the industry. So less than 1 time per month, okay, is meaningful, right? When compared to after analytics, the time downtime period has been reduced. Okay, unscheduled downtime has been reduced. And an unscheduled downtime, just you're supposed to know the difference between the scheduled downtime and unscheduled downtime. So the scheduled downtime, meaning to say we planned accordingly and then try to do it. If because of the unscheduled item means that is happened, okay, because something happened that we want to close it down and we want to monitor the things, otherwise that will go wrong. Okay, so unscheduled by downtime should not occur in the plan. Okay, energy consumption is before analytics is this much gigajoules, whereas after analytics is 850 gigajoules. That is almost 15% has been reduced. Okay, the maintenance cost is before analytics is very high, but after analytics it has been reduced by 30%. So the 30% cost reduction is very much. Okay, I mean, and am I correct or not? So if, for example, you are spending 100 rupees, I just would like to make you to spend only 70 rupees. Okay, almost 30% has been reduced, right? So the cost has been saved. Okay, maintenance cost has been reduced to 30%. Is well and good. Is a good sign. Okay, so the learning outcomes of the what you call the second case study is understand how predictive analytics is superior to reactive maintenance. Okay, learn how to combine domain knowledge with the machine learning. So you should know the characteristics of the fluid and why this is occurring. What are the precautions we need to take. Okay, what are the temperatures and things need to be maintained so that it will work well. Okay, and then try to found the reduce the fouling characteristics. Okay, these are the domain knowledge. Machine learning, how to find it out. Proper maintenance need to be maintained at what frequency it need to be cleaned. Okay, and things like that we are just trying to learn from the machine learning techniques. Okay, gain insights into time series modeling using long short-term memory. Okay, for process behavior prediction. Okay, so this is about the learning outcomes of case study 2. And coming to the discussion, so we have seen elaborately the two case study. One is on distillation, the another one is a heat exchanger. The distillation we are just trying to optimize the process. I mean the efficiency of the distillate. Okay, the purity of the distillate. What I mean is the purity of the distillate. Whereas in the distillation, heat exchanger, what we are trying to find it out how to reduce the fouling characteristics during the process. How well we need to periodically maintain the cleaning process. Okay, so that it will run at a lower maintenance cost. Okay, that's what we have seen. So here these are the real scenarios in the chemical engineering field. So how this techniques have been employed, but I didn't show you the algorithm which has been used for this process. I just try to explain in a very shallow depth. Okay, so when you want to go for a algorithm, okay, what is the algorithm we could be able to predict by using the feature engineering, converting the data into featured features, and then how to use these models. Okay, and then try to understand the algorithm which has been written in a deep learning or supervised learning, and try to compare the things that I didn't show to you. Okay, so you could very well can write the program in MATLAB or Python, using Python. Okay, so in the last week I went to what you called uh, Rajalakshmi Engineering College, actually, in fact, for data analytics, I mean, for external. Okay, so I've seen how these people have been using this in Jupyter, Jupyter Notebook. Okay, they are writing the code using the Jupyter code. Okay, Jupyter Notebook for writing the algorithm. Okay, these things you should know. Actually, I've shared material to you already through WhatsApp. Please try to look into the things. Why I'm trying to say all this. Okay, so what is the depth of the learning is another question mark. So these are the general perspective. Okay, what I'm trying to talk is general perspective, and then for your undergraduate level, the coding you just try to understand, read out the coding, because now the coding itself is very simple, becomes simple, because the people have been trying to take out from the chat GPT. Okay, so the coding is there, but at least you're supposed to know how to read out the coding. Okay, so that is a very must. And also, to be a specialized, if you want to be a specialized in data analytics and machine learning, you need to know actually how to write the code. Okay, so how this what you call it, the chat GPT has been written, just go and see the code what they have written actually, so that it will almost 80% accuracy it has been providing for any field. Okay, so how much data they have pumped into that machine learning model. Okay, it's definitely it is a deep learning, right? So the chat GPT works on the deep learning. So these are the things you need to understand the process, how this is works. Okay, how well we can be. I mean, by knowing in depth of a particular subject, you should know deeper and deeper. Okay, that's what I'm trying to say. But what I'm covering right now is not very deeper; it's a shallow one. But at the basic things, what are the things you're supposed to know when you try to see the data application of data analytics in chemical plant? That's what I would like to say. The actually this topic they have given the case studies of chemical process plant. How this need to be the data analytics techniques need to be implemented. Okay, that's what they are saying, asking, right? So the discussion goes like this. So I just put you the three questions. We'll discuss one by one. But these are very important questions actually. Okay, why should the interpretable models like random forest be preferred over deep learning? Okay, So, random forest is a supervised learning. When compared, we preferred over deep learning, interpreter models. Okay, we preferred. So, this is the question. So, deep learning obviously will give you better results. Okay, but sometimes the interpretable models like random forest, that is a supervised learning, is preferred. Why? That is a question. Okay, that we'll see elaborately here. Okay, sometimes need not be necessarily we need to go for a deep learning. Sometimes there is a supervised learning, it will give you a better thing. Deep learning actually is an unsupervised learning. Okay, it's a deep learning is an unsupervised learning. How do you balance the accuracy versus explainability in safety critical process? So, which one is, how do you balance? Okay, so whether the accuracy you are looking for better or you want to go for a explainability. Okay, that is very important. So, the explainability is supposed to have a transparency, but accuracy need not be a transfer, need not require the transparency characteristics. Okay, I will tell you actually one by one. Okay, the third part is what are the challenges in deploying the machine learning models in chemical plants. Okay, so what are the challenges in deploying the machine learning models in chemical plants that we are going to discuss one by one. So coming to the first question, why should interpretable models, that is a like random forest, be preferred over the deep learning? First one is transparency is secured. Okay, so in regulated industries like chemical, pharmaceutical, and energy, model transparency is crucial. Random forest, decision tree, and linear models, okay, all are supervised learning, provide clear logic and why a prediction was made. This is important for regulatory compliance like Food Drug and Administration, Environmental Protection Agency, auditability and documentation, gaining trust from the process engineers and operators. So when you have this transparency, okay, so why, for example, this model's clear logic on why a prediction was made, why a prediction was made. So if you give a clear explanation, then that will be easy for them for to understand the thing and they will approve the things because the regulatory compliance is very very important for the industry. Okay, when you go for some of the industries, last time the speaker who come from pharma company, our own alumni. Okay, you were Mr. Sivkumar, Dr. Mr. Sivkumar, I think. Yeah. So 2 days before when he was discussing about this thing, so the regulatory compliance is very very important. Okay, even though they are despite they have a factory over here, they will look for the standard of food and drug administration for the pharma company. Otherwise, they said actually they will give you a notice. Actually, not if it is not with the standard, they will not allow you to process further. Okay, so that means they will not allow to run the process. Okay, so the regulatory compliance is very very important, and auditability and documentation. Okay, so if anything goes wrong, okay, as a chemical plant, always the safety is very predominant important. So this need to be noted down. Otherwise, what will happen? This is not standard. Okay, if you don't maintain the regulatory agencies requirement, obviously they will not allow you to run the process. That is very very important. Gaining trust from the process engineers and operators. And coming to the explainability and accuracy, when the consequences of incorrect decisions are high, okay, so if the incorrect decision is very high, such as triggering alarms or safety shutdowns, a fully explainable model is often favored over a slightly more accurate black box model. So I will try to explain what is black box model. So the explainable model is more often favored over the slightly more accurate black box model. So it's very clear. So if the consequences of incorrect decisions are high, so for example, even though you are going for a black box model, okay, that is a very more slightly more accurate, okay, but the consequences of incorrect decisions are high. Okay, so that means better to go for a fully explainable model. So when the consequences of incorrect decisions are high, such as triggering alarms or safety shutdowns, a fully explainable model is often favored. Underline the word a fully explainable model. Because transparency, explainable model, we could be able to justify the things. Okay. Otherwise, you just go for a more accurate black box model. Okay. But the consequences of incorrect decisions are high. Okay, so if you think the black box model is giving an incorrect decision, okay, and the small incorrect decisions, we could not able to justify why you have taken that particular stand. That is very very important. Hope you understood what I'm trying to say. So now I would like to explain about what is black box model. A black box model is a conceptual framework used in various fields to represent a system where the internal mechanisms are not fully understood. Okay, please try to understand where the black box model is a conceptual framework used in various fields. Okay, here we are just talking about chemical field to represent a system where the internal mechanisms are not fully understood or transparent. Okay, so this model is not like a explainable model. Explainable model are really transparent. Black box model is not transparent, but the input and the output are observable. So by using the black box model, we could able to find the input and output and which are observable. It focuses on the relationship between the input and output, treating the internal working as a black box that is not directly accessible for examination. So the key characteristics focus on input and output. The model emphasizes the relationship between what goes into the system and what comes out. Okay. The opaque internal mechanism, the internal process or mechanism that transform the input into output are not visible or easily understood. So is a black box. Why the term black box comes into picture? Even though we are observable for input and output, the mechanism is not clear. Hope you understood what I am trying to say. So the simplified representation, it simplifies the complexity of the system by focusing on the observable relationship between the input and output without delving into the details of the internal workings. So the applications, consumer behavior, machine learning, academics, cybernetics, and so on and so forth. So coming to the machine learning, so what is the application of this model? In machine learning, black box models like neural networks, okay, are those where the internal decision making process are difficult to or difficult or impossible to interpret. So you understood what I'm trying to say. So black box model, even though is slightly more accurate, we will go for a explainable model. So for instance, so for this case, diagnosing a reactor fault with high confidence, justifying why a maintenance alert was triggered. Okay, so we need to justify why a maintenance alert was triggered, diagnosing a reactor fault with high confidence. Okay, these are the things they are highlighting here. Coming to the limited data availability, deep learning models, especially LSTM or CNN, require large volume of label data. So long short-term memory is required a large volume of label data. In cases with limited or noisy data set, random forests or gradient boosted trees often perform the deep models due to lower overfitting risk or better generalized from fewer samples. Coming to the engineering integration, when models are to be deployed in control rooms, simple models are easier for process engineers to monitor, validate, and maintain. So, what is the advantage of the engineering integration? When models are to be deployed in control room, simple models are easier for process engineers to monitor, validate, and maintain. They can view the decision rules, okay, supervised learning, okay, decision tree, examine the future importance, modify the threshold without deep machine learning knowledge. Okay, so these are the advantages of in terms of the when go for a explainable or the black box model or engineering integration is easy to follow the things. Okay, so coming to how do you balance the accuracy versus explainability in safety critical process? Okay, coming to here, hybrid modeling approach use interpretable models for safety critical decision and complex models for secondary insights. So use interpretable models for safety critical decisions. So you for safety critical decision use the interpretable models and the complex models for the secondary insights. Example, use a random forest to flag potential equipment failure and use long short-term memory model in parallel to forecast the future trends. The simpler model validates or confirms the more complex one. So the simpler model validates or confirms the more complex one. Post hoc explanation tool. Coming to the post hoc explanation tool, employ sharp or line model, okay, to provide the insight into model behavior. Okay, this method show which variables influence a decision even in neural networks. So coming to the sharp, that is shapely additive learning model, okay, additive explanations. So what does it mean? The sharp values provide a way to interpret deep learning models but attributing the contribution to each input. feature to the model's output. It helps understand how individual features influence the prediction, transforming deep learning models from black boxes into more transparent and interpretable tools. It helps understand how industrial features influence the prediction, transforming deep learning models from black boxes into more transparent and interpretable tools. So this is a sharp deep learning model. So how sharp works for deep learning? Sharp values are based on game theory, where each input feature is considered a player and model prediction is the game output. They quantify how much each feature contributes to the overall prediction. Deep explainer for deep learning models, the shape library provides the deep explainer class. This class approximates sharp values by back propagating contributes from neurons in the network to input features, interpreting the sharp values. So positively sharp values indicate a feature positively influence the prediction, while negative values suggest a negative influence. So the magnitude of the value reflects the strength of the effect. So what are the benefits of using SHAP with deep learning? One is the interpretability, debugging, model selection, and fairness. So the example, imagine a deep learning model predicting whether a loan applicant is risky. SHAP values could reveal that the applicant's credit score and income are the most significant factors deriving the prediction, helping to understand why the model deemed a loan application risky. So, hope you understood what is a sharp deep learning model. Okay, so the sharp deep learning model values provide a way to interpret the deep learning models by attributing the contribution of each input feature to the model output. Okay, and coming to the line deep learning model. So, live deep learning model, local interpretable model agnostic explanation is a powerful technique for explaining the prediction of any machine learning model, including deep learning model, in a locally faithful and interpretable way. It works by approximating the complex black box model with the simpler, more interpretable model locally, providing insights into why a specific prediction was made for a particular input. So the explanation goes like this: perturb the input. Line starts by perturbing the input data point, especially example, slightly changing an image, modifying text or altering the features in tubular data. Get predictions. If then feeds this perturbed input into black box model and observes the resulting prediction, weight the perturbations. Line weights the perturbed data points based on how close they are to the original data point. Train an interpretable model. Finally, it trains a simpler interpretable model, example, a linear model or decision tree, on the weighted perturbed, perturbed data to approximate the black model's behavior locally. What are the key benefits of using LIME? That is a local interpretable model agnostic explanation. LIME can be used to explain prediction from any machine learning model regardless of its complexity. Local interpretability and explainability. Okay, so LIME in deep learning, image classification, text classification, and tabular data. In summary, LIME is a valuable tool for understanding and explaining the prediction of deep learning models, enabling users to gain insights into the model decision making process and build trust in prediction. So, the LIME is a powerful technique for explaining the prediction of any machine learning models, okay, including deep learning models, in a locally faithful and interpretable way. So, when using this deep learning models, employ SHAP or LIME to provide insight into the model behavior. And these methods show which variables influence the decision even in the neural networks. Threshold-based safety interlocks allow deep models to make prediction but build manual override rules or threshold based on engineering principle to ensure safety. Underline the word manual override rules. Okay, even though the deep learning actually, I mean the model has been used, then the final decision has been overruled. Okay, so follow deep models to make prediction, but build a manual override rules to threshold based on the engineering principle to ensure safety. So when we could not able to test everything on the 100%. Even the material I used to say to the students, even if we try to find it out the information from chat gpt, it will understand on its own characteristic. If doesn't it make sense, whatever the information which the chat gpt is providing may not be correct, it may not be correct. Okay, I will work on the things what you are looking for, whether it makes sense, that we need to check. Okay, that's why I used to ask all my students not to simply copy the assignment from the thing, just try to understand whether it's giving a correct interpretation. I'm taking a correct question in a correct way and it giving an answer in a correct way. That we need to check in a manual thing. Okay, even though I just try to check even for myself, when I try to take some data from chat gpt, okay, through using the chat gpt, I will put my brain. Okay, so that's why our human brain is more powerful than any other system. Okay, even in advanced system, anything. Okay, because our neurons, these systems or everything works on how our brain works, right? Right, so that's why it's a neural network, right? So obviously how the neuron works, the neural network is also working on the same connectivity. Okay, so that you need to understand. So manual override rules or thresholds based on engineering principles are very important to ensure the safety. Collaborative decision making. Involve domain experts in the modeling loop. Engineers may help review predictions, provide feedback, and define meaningful constraints. Okay, so what are the challenges in deploying the machine learning models in chemical plant? This is a very, very important question. Okay, the discussion we goes like this. Okay, deploying the machine learning models in operating chemical plant presents several technical, operational, and human related challenges. Very, very important. Human related challenges. Deploying the machine learning model in real field serve the technical and operational and human related challenges. Data quality and availability, cultural resistance and trust, model generability, model maintenance, integration with the control system, cyber security, and compliance. So these are the six points which we are going to discuss about this question. So data quality and availability, sensor drift. So sensor drift, if the sensor is not working and giving a wrong value, missing data, now it's inconsistent sampling, right? Okay, so this is very important, right? Many plants have legacy systems with poor data logging. Okay, so labeling events, fouling failure retrospectively is often inaccurate. So this is one of the things we need to consider. What are the challenges in deploying the machine learning models? So if the sensor is not working and you are giving an input to the system, to the machine learning, obviously that will end up in a failure. Okay, cultural resistance and trust. Okay, engineers and operators may be skeptical of black box model. Okay, and they are not aware of it. Okay, so the requires training and involvement of plants personnel for adoption. So anything. Okay, so it's easily for manual reading, you easily can train the people. But when you want to train based on the models, okay, then you should have the people should be have a little more knowledge. Okay, and then you have a potential to do that task, right? So request training and involvement. Analyze the word training and involvement is based on the individual thing. Okay, of plant personnel for adoption. So when I say when I was in and doing my undergraduate, okay, in third year, so I have been asked to take down the reading in the reactor for every 5 minutes manually. Despite they have a DCA system, okay, digital control system, distribution control system. Okay, they have been asking to do note it down the thing. Okay, because they are monitoring both the way. Okay, manually as well as the thing. So requires training and involvement of plant personnel or for adoption. That is one of the restrictions in order to implement the deploy the machine learning models. Risk aversion. Operators prefer stable known system over new technology. So when you have been, because most of the time even in industry they don't replace the old system and then make it into a new thing. Okay, that you can everywhere in India you can see, but in the Western countries it is not correct actually. In Western countries they always prefer the advanced techniques because they have a lot of what you call money actually to replace the things and advance. But adaptation also will be little higher when compared to the Western countries. In India is lower than the Western countries because we don't accept the new things at such at the earliest. Okay, unless otherwise is the most important. For example, the mobiles. Okay, so some few things we don't accept. Okay, because we just go for a traditional conventional way. Okay, that you are not you are aware of it, right? So risk aversion. Operators prefer stable known system over new technology. Model generalizability. A model trained on one unit may not generalize to others. Okay, that is very important due to equipment differences, feedstock variation, and environmental influence. So I can say this example: equipment differences. Okay, so when I was doing my master, I've been asked to test the characteristic compound analysis of treated effluent. Okay, treated sludge actually by using advanced oxidation process by using ferrous sulfate and hydrogen peroxide. After the sample has been collected, I would like to measure the COD and BOD value and the compound which has been present inside the treated sample. Okay, after the treatment, advanced oxidation process. So when I go for a testing of this by using a GCMS, gas chromatography and spectroscopy, okay, so they have given a procedure to adapt this one, so that they have said actually the water content should not be present in the sample. That is the requirement of that particular equipment. Okay, so but it may not be necessarily the same procedure need to be followed for processing the sample before it has been subjected to the experimentation. I mean analysis. Okay, so because of the variation of equipment, the procedure of preparing the sample for analysis itself is getting different. So imagine, so if in a chemical process, okay, so the model trained on unit may not be generalized to others. So the equipment difference will obviously changes the things. Okay, that's what I would like to highlight over here. Okay, and coming to the feedstock variation and environmental influence are also the factors. And coming to another three things which machine learning models are what you called shows deploying machine learning in chemical plant challenges, the model maintenance, integration with the control system, and cyber security and compliance. Coming to the model maintenance, models degrade over time due to changing condition, concept drift, needs ongoing monitoring, retraining, and validation, integration with the control system. Machine learning models must be compatible with the SCADA or DCS. So the SCADA and DCS distributed control system, I'll explain to you. Okay, machine learning models must be compatible. Okay, that is very important. Okay, so what do you mean by DCS system? So the distributed control system is a computerized system used to automate and control industrial process. It differs from traditional centralized control system by distributing control function across multiple controllers, enhancing reliability, scalability, and efficiency. These are used in various industries, including chemical, manufacturing, power generation, and mining. What are the key features and benefits of DCS? Distributed control functions are distributed across multiple controllers, improving system reliability and making it easier to manage large complex processes. Real-time monitoring and control, DCS provide real-time data collection and processing, enabling operators to monitor and control the process effectively. Enhances safety. By automating critical control function, DCS can reduce the risk of accidents and improve the safety. Improved efficiency. DCS can optimize the process, reduce the energy consumption, and increase the productivity. So the scalability and integration goes like this. DCS can be easily scaled up or down to accommodate the changing process. DCS can also integrate with other systems such as supervisory control and data acquisition, that is a CADA system, to provide a comprehensive view of the entire application. So the DCS are used in a wide range of industrial applications like chemical processing. So this CADA is a computerized system used to automate and control the industrial process. So the machine learning models must be compatible with the DCS. Okay, so requires API development, cyber security assurance, and compliance with the safety protocols. And coming to the what you call the SCADA system. So what is the definition? How it goes? Okay, so we see the SCADA system, the supervisory control and data acquisition system, is a computer-based system that monitors and controls industrial process by gathering and processing a real-time data. It is a collection of hardware and software that allows organizations to supervise, control, and manage equipment and process remotely. The key components of this SCADA system, the sensors and actuators, remote terminal units, communication network, central server, human interface. So the sensors and actuators, these field devices collect data and execute the commands. Remote terminal unit act as a intermediaries collecting data from field devices and transforming it to the central server. Communication network, the network facilitate data transmission between the RTUs, remote terminal units, and the central server. Central server receives, process and analyze the data from the field devices. Human machine interface. Software allows operators to visualize the data, interact with the system, and control the process. What are the benefits of the SCADA system? Remote monitoring and control, data acquisition and analysis, increased automation, improved communication. So the application of SCADA systems are used in various industries, not only in chemical. Okay, so power generation and transmission, water allied industries like water and wastewater treatment, oil and gas. Okay, it's a chemical. Okay, so this is how the SCADA definition goes like this. The SCADA is a computer-based system that monitors and controls the industrial process by gathering and processing the real-time data. So this is a distributed control system. This one is a supervisory control and data acquisition system. Okay, so integration with this control system is again a challenge, must be compatible. If it is not compatible, obviously we could not be able to machine learning model could not be integrated with the DCS systems. Okay, so coming to the cyber security and its compliance, ensuring machine learning systems are secure, auditable, okay, and compliant with the industry standards like ISA 95 for automation integration, IEC 6151 for a functional safety. Because the decision, the futures, the outcomes from the machine learning, if it is not secure, obviously that will lead to the question mark for the safety of the process plant. Especially the chemical safety is very very important. Chemical process plant safety is very very important. That we already have the one subject on the process safety. Okay, so with this note, I would like to conclude today's section. Okay, so hope you understood these three important things which we have discussed in mainly on this section. Okay, apart from the case study 2. Okay, why should interpretable models be preferred over deep learning, and how do you balance the accuracy with explainability in safety critical process? What are the challenges in deploying the machine learning models in live chemical plants? Okay, so with this the case studies makes meaningful. We have done actually how to do go about it. Okay, for different scenarios, two case studies, and what are the challenges which need to be faced during incorporating these machine learning techniques into a system chemical process plant. So with this note, I stop it here. If you have any doubt or anything, please let me know so that we can see in next class. I'll stop it here. Thank you for listening. See you in next class.